In this video, we're on the top of page 86, and we are going to actually talk about some graphs and some sets of ordered pairs that are not functions. Everything that we've done to date, every graph that we've done to date, has been a function, but there are some graphs that are not. So to be a function, you've got a real specific definition that you have to meet, some conditions you have to meet. So in order for a graph or an equation or a set of ordered pairs to be a function, each input value, and remember we said the input values are the x's, each x value of your ordered pairs, or each x value on your horizontal line if you're looking at a graph, can only correspond to one output variable, one y value. For example, if 3 is in the domain of f, meaning 3 is an x in your domain, then f of 3, when you plug in 3 for all of your x's, your answer may not have two values. They need to have a distinct value. And I'll point out some of these examples as you go along. But in other words, to be a function, the x values cannot repeat and have different y values. Another way that we can tell by looking at a graph whether it's a function or not, we can do what's called the vertical line test. And that is taking a vertical line and placing it anywhere in your graph and having it intersect in more than one point. If that's the case, then you don't have a function because you have an x value that has two y values associated with it. So if you look at example 2a, here's a circle, and if we apply the vertical line test anywhere in the graph, if you can draw a vertical line, I'm trying to get it pretty straight here, I'm not doing a good job. Darn, let me see if I can do a better job with that. You can see if you draw a vertical line and go directly down the point where x is equal to -2, you have intersected two specific y values, which means if you were to write these two ordered pairs, they would say -2 and positive something, whatever this point right here represents, a positive something, and this point down here would represent -2 and a negative number. So our rule says to be a function, you can't have an x value that's got two different y values. So we could say easily this is not a function, and we could say does not pass vertical line test. And there are a number of places, obviously a number of vertical lines that you could have drawn that cut through this circle both at the top and at the bottom, but at the same x value. So that's a pretty easy one to look at and go, nope, not a function. What about this one? So this one is a parabola. We know that's going to be an x squared equation. If we were to try to write the equation, it would have an x squared in it. And I'm looking and I'm thinking, well, maybe you think it doesn't pass the vertical line test because you're thinking that maybe all of these points are different and all go to x is -3. But that's really not the case. Every single point, and this graph goes on forever and ever, every single vertical line that you would draw on this graph, I don't care how close it is to the next point on the graph, it would have its own unique y value. So this is a function because every input, every x, has a unique y value or output. Okay, let's go on down and look at a couple more. I think I've got a couple more examples down here. So if you look at y is equal to 2x, you might need to think a little bit harder. You don't have a graph to look at, so you can't use the vertical line test. But you're trying to ask yourself, if I put in a number for x, is there a possibility that when I put in that same number for x, I'm going to get a different y than I did the first time? And I think you'll, by picking a few points and seeing what's happening here, I think you'll see that if you put in 0 for x, you always get 0 for y. If you put in 1 for x, you're going to get 2 for y. There is no time where you're going to put in a 1 for x and get something other than 2. So I think we can say, yes, it is a function. Because each x has a unique y that's not going to change if I put that same x value back in it again. D is a little bit different. It has, instead of the x being squared, it's got your output being squared, y squared. And what I try to do is I try to pick an example that rules out it being a function. And if I can pick one example, then I can say, nope, not a function. So what I see in this equation is I see, let's let x equal 9. If x is 9, then y could be -3, or y could be +3. So if x is 9, then -3 squared would be 9, and +3 squared would be 9. So if we wrote these as ordered pairs, the x is 9, and one of the y's is -3, and x is 9, the other y is +3. So I think you can see that this is a case where our input doesn't have a unique output. Our input actually has 2 possible outputs. So this is not a function. It's a graph, it's an equation, it's all kinds of things, but it is not a function. And then finally, let's look at these 2 sets of ordered pairs. These I think are really easy. Matter of fact, these are probably my favorite way to be given the chance to say whether it's a function or not, because all I'm looking for is, are the x's unique to the output? So the x value does not repeat. So 0 can be 5, 1 can be 5, 2 can be 5. It doesn't matter if your output repeats. That's perfectly fine. What can't repeat is the x value, like in this example, with a totally different output. So this guy has unique x values, and we don't care that the y values repeat. So yes, this is a function. And if you were to graph these points, by the way, you'd see that it passes the vertical line test easily. And then finally, F is an example of where the x values do repeat. And they've got, in this particular set of ordered pairs, they've got 3 different outputs, 3 different y values. That's like our example number D. So this is not a function because your x cannot repeat with a different y. So this is not a function. Okay, and we'll do a couple more problems on 4D on the next video. Thanks for watching.